Hey, good morning, everybody. Thank you for joining us for this pre-proposal conference for development of microgravity food production, plant watering, volume management, and novel plant research on the International Space Station. As I'm sure you've seen, this is going out under a ROSBio solicitation in NASA's Space Biology program. And so we're very grateful to David Tonko and his team for supporting us. But I am Molly Anderson. I am not typically part of the space biology world. I work on environmental control and life support systems, and this is being supported through the AES habitation system. Next slide. So this Appendix C is a collaboration between Space, Life and Physical Sciences Research and Applications, the Flipchart Division, and AES. Our goal is to generate, in the end, a pick and eat food production system that we can use for future exploration use. So the goal of this collaboration and this solicitation is to get a research and development project that leads to the development of things that fix our key problems with gas. And that is a more reliable water and nutrient delivery approach and a volume optimization approach. And so in this phase A, part of this solicitation, we are looking for proposals of the plant water and nutrient delivery system for microgravity. They need to provide sufficiently uniform wetting of the roots, not allow the release of free water into the cabin in microgravity, and yet still allow sufficient aeration and oxygen to get to the roots. We are also looking for plant spacing systems for these edible plants to optimize volume. You can propose to one or both tracks in the content that you provide us in your proposal. Okay. Ben, do you want to take a minute with the computer sound? Okay, let's see if this is any better. I'm going to move on to our introduction to space biology on the next slide. Okay, so since this is a collaboration, we are hopefully supporting the interest of the space biology program within their decadal survey. They are interested in plants and microbes and how they contribute to food life support. And the food system is definitely a part of supporting human life, but is also very much integrated with the life support system of a vehicle in terms of controlling atmospheric humidity, providing clean water, providing oxygen, dealing with carbon dioxide. And so the larger your food production system grows, the more deeply it is tied to the life support system of the vehicle. So you can't prevent the plants from processing carbon dioxide and creating oxygen. and the amount of water that they use is a very large contributor compared to the rest of the vehicle. Give me this. Just as a test, can anybody hear me if I use this way? Okay, I'm giving up on the phone and I'm talking to the computer. So let me check over here. I swear you haven't missed that much. Oh. All right, well, we're gonna do them both. Okay, phone and computer. Let's see how this goes. Hopefully I haven't ruined everything. Okay, so Ben, we can tab back one slide if we would, or two, I guess. Okay, so catching up, you're here for this solicitation. We are trying to solicit the R&D projects that lead to the reliable water and nutrient delivery approach that will be used in a future pick-and-eat food production system. I'm sorry, guys, we either get you can hear through the computer, but the people on the phone can't hear. I don't know what else to do. I'm talking through both methods at once. You can propose to either the watering and nutrient delivery system path and the plant spacing system path. You don't have to propose to both, but since we need these to come together in the end, you have to be thinking about both sides as you're working through it. Okay, next slide. Somebody else on the line does have an open mic, though, and they could mute. So since this is a collaboration through Space and Life Sciences, we are trying to serve some of their interests as well. They're interested in how biology contributes to closed-loop life support. And in their plan, they are attempting to develop the scientific and technical foundation for safe, productive human presence in space for extended periods and preparing for exploration. So we think that this collaboration will help turn some of that basic science that we've done on the space station so far into useful capabilities for future missions. Next slide. Let's go to the black ones. And the next one. Okay, so switching to sort of the other side of this collaboration is our life support systems group. This is just overall for life support. You know, we're trying to work on capabilities in our ground systems and on ISS that we will then deploy in future LEO platforms. We'll be able to utilize those capabilities on the lunar surface and eventually create reliable systems for the Mars Deep Space Transport Vehicle and then a regenerative life support system on the surface. Next slide. And so when we look at this for food production, this solicitation, we're really starting over there on the left side. You know, on the ground, we have the ability to work on our crop production concepts and strategies. We're still in 1G, and we're still in a protective magnetic field. We want to deploy those to the ISS, where we will get long-duration testing, where we can really evaluate the systems, see what challenges they have, see which ones successfully provide solutions for this pick-and-eat system for crops. That's really where we get that microgravity test bed, which is so hard to achieve any other way. You are still in a protected magnetic field. So we expect that, you know, the next things NASA will do in the, in the next decade will include the gateway and lunar surface, where we'll really get that radiation environment, that deep space radiation environment.
looking at storing seeds for long durations, or how do things grow for long durations. And then in the end, we'll be able to put the two of them together and have a long duration microgravity radiation tolerant system for Mars transit, and also be able to use it for Mars surface. Next slide. So our food production vision is really looking, to provide food system security on these long duration missions. Nutrition is critical to human health and performance. We need to provide safe food. We need to provide nutritious food. We need to provide acceptable food. We need to provide variety to the crew diet and make it appealing. Because if the crew doesn't want to eat the food that we provide them, then it doesn't matter how much nutrition we packed into those stored supplies. So we're really thinking that the fresh food will be an important component to making the whole menu more desirable, as well as filling those nutrition gaps. And then there's a lot of psychological benefit, which we're not always great at measuring, but seems to be strongly repeated by the crew members we have, and other people in other constrained environment conditions. Next slide. We think that the prepackaged food system is potentially going to have some nutrient gaps if it has to be stored for the 3 years or more that are needed for a deep space transport mission. We also think that the fresh foods provide better nutrient delivery to the human body. We still are trying to limit to the pick and eat crops. We think they give us a pretty strong path to providing those nutrients, but we need to have minimal processing and preparation on the vehicle. Even cleaning food in microgravity is challenging. And then we need to find a system that will be able to
Hey, Molly?
Yeah, I think my laptop is connected to box to the Windows. So anybody who's online on the laptop.
We can switch back to the phone if you like. But
Try again.
Be good to go, I think.
All right. I have a little green microphone again. Okay, so as I was saying, we need food that fills these gaps, is good for nutrition, but fits within the constraints of the spacecraft. Doesn't require a lot of preparation, which is why we're sticking with basically things that can be consumed raw. And we're trying to achieve systems that minimize their use of mass, power, volume, water, air, and all of those important characteristics. Next slide. All right, so as we have been saying, our system needs to demonstrate that it's going to be sustainable, that it's going to have reliable performance and high productivity in order to be accepted as part of these missions and these vehicle concepts. Once we demonstrate that we can actually pull this off, then the teams at NASA setting the diets and the food systems will be able to set targets for how many calories they want to produce from this kind of food system. So we aren't specifically saying we need a food system that produces X salad or so many potatoes or anything like that. We're trying to develop the capabilities. And then once we have this efficient system, hopefully, and have demonstrated that it works and it can be a critical part of the plan, then hopefully we'll be able to get those resources committed in the deep space transport and other future vehicles. Next slide. So why did we highlight watering and nutrient delivery as one of the important paths of this solicitation? So we have grown plants in space before. We have eaten plants that were grown in space before. But it's not necessarily on the path to a sustainable, positive mass trade food production system. So on the left, we have a picture of the LADA unit. There's salt buildup. And there's microbial growth on the little felt separators. This is probably not a reusable system. This was used to grow wheat. And so if you have to throw away that box every time, you're going to be carrying a whole lot more plant production hardware than you're going to get back in food you can actually eat. On the right, we have potato tubers being grown in the astroculture unit. Potatoes are really on the hairy edge of pick and eat. They could probably be just heated in a food warmer. But you can see the arsolite media. Any of you who have dealt with flying systems in space before know that FOD, foreign object debris, is a huge problem. Particulate in the crew members' eyes is a big hazard. So loose media is going to be a big problem. And then if you imagine yourself in microgravity with potatoes buried in this box of media, how on earth are you going to get them out and then clean and reuse the media? That seems very challenging and a possibly not tenable path forward. So that also seems like something that's going to end up being largely disposable, if it's even acceptable at all with all those particulates. Next slide. Here we have, on the left side, we have the veggie unit, which is, we want to say reasonably successful. We have grown food and the crew has eaten it. On the picture on the leftmost, you can see these red lettuce leaves growing out of individual pillows. So the one on the far left, you can see that plant did not successfully establish itself and grow to maturity. You can also see some pretty big variations in the size of the plants that did make it to be established at all. And on the right, there's some more. That's a particularly tough run in veggie. We have 2 or 3 that aren't going at all. One that's growing much faster than the other 2 that are left. So veggie was intended to be a passive watering concept. There's media packed in those pillows, so it can't escape. But it has not really been reliable. Sometimes there was too much water if the pressure is high, and we ended up with fungal growth on some of the plants, or not enough water. And so now the crew is having to water things manually, which is a lot of time. And if you're attempting to scale this up to substantial amount of food production, if we're sending our crew members to Mars, we want them to be doing Mars exploration, not spending all of their time gardening. And also then those pillow packets are disposable and a lot of wasted mass. On the right, we have the ponds system growing in under the veggie lights. This was an attempt to fix some of the veggie problems with another passive system. There's still a solid media core. There's a reservoir of water, and it's supposed to wick into the core. So we're hoping we'll get more reliable performance for this for the sake of, using veggie as a research platform. But still, each of those units is effectively disposable, and you can imagine that they weigh more than the greens that you're managing to produce from them. So that's not sustainable for mission planning and packaging your mass and your stowage and all of your logistics. Next slide. And so here we have pictures of I'm going to say biomass production system and the advanced plant habitat. There are a number of things you can put in the advanced plant habitat, but let's see. The far left and the far right are actually the BPS. And so on the left you can see the guts of it, where there's a porous tube through which the water flows, can be pressurized, that then flows into a bed packed with media. Just to the right of that you can see, I think that's Oscar, preparing the APH. And so again, there's porous tubes, they're being filled with media in the area around them. Then there's a sort of retention layer, that black with all of the little holes drilled in it. And then you can see them placing the seeds in between those felt wicking layers. And so this is pretty reliable in terms of getting plants to grow so you can conduct experiments, but still not necessarily perfect. Here we have a picture of guttation with droplets at the edges of the leaves. The APH at least does use thermoelectric cooling to capture water and recycle it back in so that you don't have to utilize the entire ISS water processing system. But we still need to practice some management of all of this in microgravity for our long duration system once we pick a watering system that is sustainable, reusable, reliable, the plants grow, and then we'll optimize our control. Next slide. So why did we select volume optimization as an important track? So this is a graph that was done looking at the costs that would be associated with attempting to continuously produce some salads for crew members using veggie in an ISS module, which is honestly probably a pretty fair analog for a deep space transport system. There are other concepts out there for spacecraft vehicles, certainly, but they also need proving and developing. So the gray bar is the primary structure, which is the shell of the vehicle, or the gray section, and the darker orange section is the secondary structure, which is here is the ISS racks. So this is all converted into equivalent system mass, where we say, okay, you took up half the mass, you took up half the volume of the module, well then half the mass of the module is your fault. You took up 10% of the power generated by the solar panels, well then 10% of the solar panel mass is your fault. So we convert these all into one set, one parameter of mass. And the things directly related to the volume the system takes up, the primary structure and the secondary structure, massively drive the cost of the system compared to the power consumed and the growth chamber itself. Okay, next slide. So hopefully I've convinced you that both the reliable watering and the volume optimization are important for creating a system that mission planners and spacecraft designers are actually going to be willing to fly. This solicitation is part of our grand plan. Phase A, which is what you'd be proposing for now, is a smaller piece involving describing your concept and demonstrating key components and experiments. Phase B, in which you have to have both the plant watering and nutrient delivery and a plant spacing system to optimize the volume. That's more focused on a system prototype level. Since this is a cooperative agreement, we're expecting that NASA will furnish a place to test these with LED lights. Like, we don't feel like there's a major technological gap in creating LED lights. And other, condensing the water from the air and recycling it back. That's something NASA has done in microgravity pretty successfully. So we want to provide and work with you on the pieces that we think have been pretty reliable and we can reuse, and really focus on getting your help on these key gaps that are making our systems unreliable and unaffordable. So during phase A, key components would be validated through modeling or performance testing. And since this is a collaboration with SlipSthread and a ROSBio solicitation, we are interested in scientific experiments and investigations that validate the operation and the ability of this system to support future research and development. So we're not looking for scientific investigation. We're looking for you to use science to prove that the system works. Okay, next slide. Once we have key components demonstrated in phase A from several promising teams, we will down select to probably 2 teams to go into phase B for the development of this system level concept. Like I said, we do expect that between phase A, which is small, and you are allowed to really concentrate on only one aspect that you think is particularly challenging or enabling, you would have to modify your team to pull off then a phase B proposal. So the down select, it doesn't mean exactly the same team leads, we presume, and continuing the key technologies that you've demonstrated in phase A, but it's clearly going to be a little bit different. And then phase C is not within the ROSBio solicitation. Phase C would be a separately generated procurement contract, basically, to get hardware based on phase B to fly to the ISS. It would not be done as a cooperative agreement. It really needs to be a contract to get hardware and pass all the NASA processes. Okay, next slide. I want to emphasize, I'm not going to read all of these with the time that we have. So one of the things we changed in our appendix compared to the generic ROSBio solicitation is the selection criteria. This is a step 1, step 2 process. The step 1 is due pretty soon, but it's a relatively simple gate to get through for an invite or a decline. In step 2, though, we're going to be using a peer review panel of subject matter experts to evaluate several criteria. So significance. Is it responsive to the solicitation? Are you giving us water and nutrient delivery or plant spacing? Are you demonstrating how you're advancing the technology and any scientific knowledge through doing your project, as opposed to just giving us back this state of the art? And what is the effect of these projects on technologies, methods, or products? How much better is this new system going to be? Next slide. And then the technical approach, right? Demonstrating a clear understanding of the problem and a clear definition of the objectives of your effort. Utilizing fundamental principles in previous research. This includes both physical science and biological science, right? Physical science, fluid dynamics, fluid physics, microgravity, fluid flow, all of those things are clearly very important here. But you're going to need biological science to understand what the plants need to successfully grow so that you can provide that, and to be able to evaluate whether they are doing well. Demonstrate understanding of the state of the art so that you know that you're moving beyond it, right? And so that we know that you're not just repeating things that have already been done. Figures of merit and performance parameters, and describe how they will advance and how you'll validate them. You know, you're going to need these descriptions of how much better your system is than the state of the art in order to compete for Phase B. In any technical plan, you know, identifying technical issues and critical risks, and that you have mitigation strategies so you can successfully complete your project. Describe, you know, plans for collaboration and cooperation with NASA, since this is a cooperative agreement. And, you know, if you're including experiments to validate this system, you know, successfully or sufficiently describing them and designing them well. Next slide. Yeah, schedule, investigators and team, you know, environment, where are you doing the work? Those are all fairly standard sorts of criteria and proposals, so I won't dwell on them. Next. And just emphasizing, like I said, this award will be a cooperative agreement. Phase A will be up to $225,000, up to 18 months performance. When you complete Phase A, you would also deliver your Phase B proposal, also a cooperative agreement, but a much larger award, because we expect you know, these system level demonstrations to be happening. And like I said, Phase B has to give us, you know, the system that is both successfully going to provide the water and nutrient delivery in a way that optimizes volume. Okay. Next slide. And just timeline highlights. You can read these in the solicitation. Next slide. I think that's it. So I apologize for all of the tech support issues. I think we had two. My Wi-Fi blinked, and then NRES's Wi-Fi blinked. So we will take questions. I think we're going to expand the chat window and be able to read them. How long is the Phase A proposal? That is in the solicitation. I don't remember it off the top of my head. There are page limits for each section provided. So let's see. I'd say, okay. Now this conference is recorded. I think things are going to be posted on the solicitation page. The IP rights are should be described in the ROSBio appendix. Anthony says 20 pages for the proposal. The 5 pagers for the step 1, which is just the invite or decline gate, not the full proposal, step 2 for actual selection. Okay. Plans to collaborate with NASA. There are a very short list of NASA people who are behind the firewall for this solicitation and not allowed to talk to you about it, but you are able to contact and develop plans with anybody else you want to. We do describe, like I said, how we want to provide, you know, the test chamber lighting and aspects like that, because we're going to be providing those when we get to ISS. But other collaboration, you can talk to people and develop plans and relationships in advance as much as you would like and are able. No, the main goal of this project is not an ecological chamber on a CubeSat nanosatellite. It is to produce food for people to eat on the space station. We are focused on pick and eat crops. We have not specified particular cultivars or anything, but basically things like leafy greens, things like tomatoes and peppers that set fruit, and possibly some things like carrots or radishes, that do grow in the root zone, but can basically be eaten raw. Frankly, an aquatic plant so this is a microgravity focused solicitation. So we have ruled out aquatic plants and automatic harvesting. I think that is a bridge too far for microgravity right now. We are just trying to get lettuce to grow reliably in order to be considered seriously for future missions. What are the requirements for groups needed for submission? I think I'm going to have to refer you back to the solicitation details for that. I don't have the technical answers for that right now. You can't talk to me, you can't talk to Dan Barta, you can't talk to Ray Wheeler, you can't talk to Ralph Fritchie, you can't talk to Jitendra Joshi, you can't talk to Robin Gatens. Right now, for electrical power and things like that, we're expecting the system to be, we need it to be, kind of modular, so we could deploy a small set to try and then grow it up. So we aren't putting a hard limit on anything like that. Right now, like I said, in phase A, we want to make sure that your watering system works physically, and that volume optimization works, and then we will, since it's a cooperative agreement, work with you on how we integrate that into a system. There is not a mass target for vegetable production because we want this to be modular and scalable. Depending on how affordable it is, we'll get more or less in a mission. We are expecting about 5 phase A projects to be awarded. The 225 is a ceiling for phase A. I am not aware of an explicit age limit. However, you do need to look at the requirements for being able to submit. Plant yield or plant yield versus water nutrient input, the better metric. Let's see. That is a little bit tricky because it depends on what watering method you're going to pick, how important the cost of the water is. We do want to capture condensate and send it back into all of these watering systems, so that will help the water, the cost of the water in the vehicle because the transpiration rate is so high. No, the development of a catalyst that can make water in space does not fit under this solicitation. Microgreens are acceptable as a vegetable. We are looking, to be able to grow more than just microgreens. However, they are certainly an interesting candidate as part of trying to optimize volume. But remember, we're looking for the system that produces them, not so much the crop selection. Let's see, I think I'm caught up. Right. Dimensions in phase A are not a concern as long as it is scalable. For the phase C ISS demonstration, we are trying to get half of an ISS rack, or a full rack, which is sort of something the size of a refrigerator. We're expecting that in phase A, since it's not a huge award, you're going to be doing small demonstration components. If you want to do a big thing, that's fabulous. The chambers are quite large. You can Google NASA ISTP, International, ISPR, ISS Payload Rack Interface. It's the common method of accommodating systems and hardware on the space station. Let's see. Foreign institutions that do not collaborate with U.S. scientists. Rihanna, are you going to jump in on that one? I don't believe we can give funding to foreign institutions. We're double checking them. Okay, let's see. So if you're on the physical science fluid dynamics part, honestly, condensing the water on the wall and putting it back in the tank is the easy part. What we're worried about is getting water and oxygen to the roots. So we are interested in multidisciplinary, collaborative kind of work. So you should probably talk to somebody who can tell you about what the roots need. On the Earth we have the hydroponic systems, but the water drains away, and air is still able to reach them. Which section of the NASA technology roadmap does this best correspond to? Probably, if the old ones would be TA06, but we're updating those, so we're not really hanging on hard to any particular 6 dot whatever. Insufficient nutrition is one of the risks on the human research roadmap, and the inability to successfully grow the plants is going to contribute to the insufficient nutrition if we don't sort that out. Yeah, if you really need to look up TA roadmaps or something like that, you can still email questions to NRES, and they could get posted in the FAQ. Okay, let's see. Anthony, I just typed in a list of names. You can tell me if I missed anybody. We don't have a hard metric for crew time needed for system operation or maintenance. We would like it not to need daily intervention by the crew, so that it, eventually could be semi-autonomously operated. But there's some system level design questions that would have to be solved, in phase B, really, once you prove that the watering and the volume optimization successfully works in the first place. Oh, I guess the firewall means we can't collaborate with you. Obviously, I can talk to you about the solicitation, as can the rest of us, or, from a official FAQ point of view. Yeah. That looks like somebody's shouting out for teaming. Let's see. I guess Anthony and Rihanna, we should probably put some center points of contact if we don't have them for contacting the major relevant NASA centers here. Presumably Kennedy Space Center is the primary entry point. Johnson Space Center, maybe Marshall Space Flight Center also could have an Ames Research Center. Glenn, certainly on the fluid physics side. I believe the FAQ is on the NSPIRE solicitation page. Yeah, you really provide, yes, the team can change between the go, no-go gate for a full proposal and the final phase A. Because we don't know entirely who's on your team necessarily when you get through the step 1 gate. So that would sort of be invisible to us. Is, oh, there we go. I missed a couple people on my firewall list. Okay, is there a limit to the number of proposals submitted from one group? I don't know that we've explicitly said that. They would certainly need to be, you know, distinct technologies, distinct teams and concepts. Let's see. There is not an explicit age limit, but you have to be able to meet the other requirements of the proposal. Yes, initial planting by crew is acceptable on this stage. We're not expecting a fully automated system, just one that doesn't require, is more reliable, doesn't require constant babysitting to fix its failures. Okay, we're about at 11. No degree of automation is expected for phase, well, yeah, no degree of automation is expected for phase A. If you're doing volume optimization, you may have automation proposed as part of it if that's, you could demonstrate it if it's important, but if it's mechanized and can be automated later, that's probably sufficient. You are required to provide NASA a final report at the end of phase A. There is no minimum age. There is not an explicit TRL requirement here. Yes, we hope you publish your results. No, there is no target for mass production. It's more about getting your efficiency of mass production better than the state of the art. We expect it to be scalable and modular. We are not planning on extending phase A. It's a really short write-up. That's all I can offer. I think we're coming about to the end of the hour. I know I'm running out of time. Rihanna and Ben, is there anything you want to say to wrap us up? I know you can still submit questions about the solicitation to NRES and us, and they can go to the FAQ. How much detail? Enough to justify that your system will work. All right, well, sorry for all of the problems we had. I look forward to probably hearing more questions through the FAQ, and good luck to everybody.